The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
So we have Professor Arvind today going to talk about how actually do parallelism much closer to hardware and all the work they have been doing.
So first, just a clarification. This talk is not really about any techniques. This is some very preliminary ideas that I have some new ideas on parallel programming. The second thing is 5-6 years ago, I was going around the country giving a talk why hardware design can't be left to hardware designers. Because I think there is the way they express their ideas is very, very low level from software point of view. So I have worked pretty hard on injecting some fairly sophisticated ideas from software into hardware design. But it often happens when you deal with, powerful people, you get affected by it. So I have sort of come the full circle. Now I'm going to show you how hardware design can influence software design. And that's really the idea behind this talk. So that's hence borrowing some ideas from hardware design. Just a cell processor is a very good example of a system on a chip. And this is what everybody believes the future will look like. That you will have fairly symmetric things in some sense. And that is needed by hardware because hardware gets out of hand, if you have wires running all over the place. So people would like these things to be fairly, regular in some sense. But that doesn't mean that, all these tiles have to be the same. So for example, you may have very application-specific blocks, on your chip. So for example, in your cell phone, you have many, many blocks which are specialized, especially all the radio communication. Because if you did that stuff in software, you may not be able to meet the performance, and even if you can meet the performance, your battery will drain instantaneously. I mean, it just takes too much power to do that kind of computation, in software. So for various reasons, we need application-specific processing units, and I'm sure cell processor has quite a few of these. Then we need, by the way, these application-specific units are often called ASICs, and you can think of them as a separate chip, but in due course of time, they become blocks of a bigger thing. You may have general-purpose processors. Already, systems have more than one such thing. Cell processor has how many? Like 8?
Depends. It has some have 8, but they don't get yield. So the current PlayStations have either supposedly 7, but we decide only 6. So the way by the yield basically cut down the amount of things we get.
And high-end cell phones have, 2 general-purpose processors and 2 ARM. General-purpose processors and 2 DSPs on it. So you will certainly have, multiple processors. You will have memory banks, etc. And you will have structured on-chip interconnection networks. So I think this is a little bit, this is not controversial. That this is what the trajectory will look like in future. That doesn't mean that all the chips will look the same. You may have different mixes of things depending upon the application. And one of the interesting things is, can you put together one of these things fast enough? Because it's very, very expensive to design and implement these things. So really the one issue that comes up all the time is, can we rapidly produce high quality chips and surrounding systems and software for such things? So this talk, as I said, it's about ideas, and what I'm going to do is I'm first going to tell you how I used to think about parallel programming, and then I will, and this way it's all about threads, where are my threads? And I worked on this problem for very, very long time, like, 20 years. And this is not necessarily wrong. I mean, I'm sure in this course itself, you have seen quite a bit about this. And I think tomorrow's lecture is on silk, so you will see even more about threads. And lately, I've been thinking about it differently. And really the main point I would like to get across somehow to you is now I think of a parallel programming module as a resource. What do you mean as a resource? I'll try to make it more concrete, this idea. And the whole issue here is I think this viewpoint is valuable, but it's not proven yet. So it may not be right. So just a warning. I've been working with this on students, Nirav Dave in particular. Now, those of you who have heard of transactional programming, lots of things I will say, you'll say, oh, you mean a transaction? Yes, so there are very, very strong connections with transactional stuff, but that's not the language I'm going to be using here. These slides are color-coded. So when I'm talking about old way of thinking, it's yellow. And when it's new thinking, then it's white. So I think you probably have already heard this, that the only reason for parallel programming used to be performance. This made programming extremely difficult. You had to know a lot about the machine. You were programming and codes were not portable, endless performance tuning. All this still goes on. Very few of these things have changed, right? Parallel libraries were not composable. And this is one of the main things I worry about a lot. And I think Alan was alluding to it too. Somebody has code, he just wants to run the damn thing, even if factor of 2 speed up would be fantastic. Often it runs slower, when you run it on parallel machines. Very difficult to deal with heap structures and memory hierarchies. And then there is always this synchronization cost issue, In some sense, parallel programming doesn't make sense if there is no synchronization going on. That's like just embarrassingly parallel computation. You just start off and things, they never talk to each other. In even moderately interesting parallel programs, there is always some communication, between various tasks. And when that happens, then synchronization cost becomes an issue. And it is such a major issue right now that you have to think about it upfront. Oh, if I synchronize too much, then I know for a fact that my program is going to run like a dog, right? So you try to avoid synchronization and make things coarser and so on. Really, the whole issue used to be how to exploit hundreds of threads from software, because new hardware will support many, many threads. But at the same time, it's important to understand that in this world, there is always virtualization. So the number of threads in your machine is never going to match exactly what you have in your application, right? So any programming model you have, virtualization is a very important aspect of it, that I have n threads, and n may be dynamic, maybe varying with time, in my application, but in hardware I have some fixed number of threads, right, which is significantly smaller in general than what you have in your application. So the thing I was most interested in all those days was what I call implicit parallelism, and from the questions I was hearing about analysis you're doing of your programs, all those issues come up there. Given some code, can I figure out, what can be done in parallel and just run it like that? So extract parallelism from programs written in sequential languages, and people like Saman are champions in this. And I have also spent lots and lots of time on this research problem. So this is one of those areas which certainly has not suffered because of lack of research. There is tons and tons of research in this. You can go to IBM and there will be 50 PhDs working on Fortran compiler, trying to extract parallelism, right? So, but the success is limited. In fact, the main takeaway from this research is people have learned now how they should write their program so that compiler has a chance of extracting parallelism. Because now people look at your code, they say, well, no, this is a bad code. Why? Because compiler can't analyze it, right? So it's sort of you become part of the equation in this. Now, the methodology I was pushing for a long time was functional languages, programs in functional languages which may not obscure parallelism in the first place. I'm not going to talk about functional languages, and it's immaterial, whether this is a good idea or a bad idea. The fact of the matter is, in real life, people's reaction is functional languages. Are you kidding me? Right? It's sort of so it doesn't get off ground. right? So it's one of those things I can come and preach to you. It's good for your soul, where they say, leave me alone, I don't do movies and, with subtitles, right? Yes.
Sorry to temporarily derail you.
Sorry?
Sorry to temporarily derail you, but so what kind of parallelism is easier to extract from a functional language? So I mean, I can clearly see some task parallelism. Is it also, can you also extract data parallelism or pipeline parallelism or whatnot?
I think it turns out that's actually not the right question to ask in the functional language sense, because functional language doesn't obscure the parallelism that was there in the first place. So you already have a partial order on operations as opposed to a sequential order. You see, when you write in Fortran, even a simple thing like, f of g of x, h of y, right? It may be obvious to a functional programmer that these things can be done in parallel. Perhaps the execution of these can overlap with the evaluation of f. But that's not the semantics of Fortran or any other sequential language. The semantics is you're supposed to execute the program left to right, top to bottom, right? So you will go and execute G first, and you'll go inside G and execute it, and then you will go and execute H, and then you will go and execute F in that. Why is that important? Because there are side effects, so it's conceivable that, you do something in this which affects this, and so on. So you're given a sequential order, and then compiler does deep analysis, the kind you're doing right now in terms of dependence and anti-dependence and so on, right? Which says it's okay to do G and H in parallel. While if it was a functional program, then by the semantics of the language, G and H can be done in parallel. That doesn't mean it's a good idea to do it in parallel. So when we get to the second point of mapping this computation onto a given substrate of 2 processors or 10 processors, then problems become similar. But the problem of detecting parallelism is very different, because you don't talk of detecting parallelism in functional languages. It's already there, You don't obscure it. Does that make sense?
Yeah, maybe.
And it goes without saying that, if your algorithm has no parallelism, then functional languages or any other language, there's no magic, right? You can't suck blood out of stone. So you have to know your algorithm. You have to know whether, what operations can be done in parallel, right? So language only is an aid in some sense that if it was parallel, I could express it more easily as a parallel program, right? And if it's a bad language, you obscure it and then you try to undo the damage. Now, as I said, there has been a lot of success in this in terms of dense matrix kind of stuff, but more irregular the computation, harder it gets to do these things statically. So, when you can't do it, then people, of course, design explicitly parallel programming models, and some of the most successful ones in this are data parallel. And you will hear about multi-threading tomorrow in Silk. And then there are very low-level models where you're doing actual message passing, between various modules that are sitting over there. And I can expose you threads and synchronizations at a very low level, fork and join, etc. So, of course, higher level models are preferable because you're likely to make fewer errors in them. The question is, can we compile them? And in some cases, what turns out is like this is a good model, but it is not general enough. So if you have a data parallel algorithm, fine. You should use these things, but not all applications fit the data parallel model. Multi-threading in some sense is more general. This is what I mean by a multi-threaded model, that you may have a main which spawns off things. So not only these things can be done in parallel, but execution of these can overlap with the execution of F. So parents and children may be executing simultaneously. So if you look at this as an activation tree, this invokes a loop, which has many, many iterations in it. When we talk of sequential computing, you're always sitting on one branch of this, right? So that's the stack, this stack, stack frames, right? When you talk of parallel computing, then part of this activation tree is concurrently active, right? So all problems get harder. I mean, storage management gets harder. And what gets especially harder is that there is this global heap, right? You always have heap in interesting programs, global data structures. Now the problem is if this and this are active at the same time, or this and this are active at the same time, and they are both reading and writing into the data structure, then naturally there is a race condition in this. Even if only one guy is writing and 5 people are reading it, it's a question of the guy should not read it too soon. So the moment you do any kind of parallel programming, synchronization issues arise immediately. You always have to worry about how do I indicate that it's okay to read this? Well, you can follow some control ideas. You say, this guy was writing, he has finished execution, so it must be okay to write. Or you can go to very fine-grained synchronization. You can have some bit here which says, oh, this data has been, updated now. It's okay to, unlock it and read it, and so on. So all these ideas have been explored, and they're still being explored, right? In this context, the main takeaway is there is, instead of a stack, you will have a tree which is active at the same time. Many things are going on. And the second thing is that there is a competition. There is a race in reading the heap data structures, and therefore you have to worry about that you don't read it too soon, or you don't write it too soon, because if you write it too soon, you may clobber before somebody else gets a chance to read it, right? So these issues are quite serious. Now, it's really possible. I mean, I claim, I have languages which can express computation very efficiently this way. Efficiently is not the right word. Very easily you can express computation in this way. But at the end of the day, the goal is to take that stuff and run it somewhere on some parallel machine. Whether it's cell processor, in the old days, it would have been, parallel machines of various ilks. And that has proven to be quite difficult. Efficient mapping of these things, because it turns out that you say, oh, you didn't tell me before you have only 2 processors. Then I would have, expressed the computation differently, right? Or you didn't tell me that you have 1,000 processors. So there is this kind of, yes, there is virtualization, but it's not virtual enough. Qualitatively it matters a lot. What is the target, and that affects how you would have expressed the computation. So I used to go around saying this all the time, that parallel programming is so important that really sequential programming will be taught as a special case of parallel programming, because it will be all parallel, right? And if you have only one processor, then we can teach you some special tricks how to run it efficiently on one processor. So this, as you can see, is largely an unrealized dream. So
that's an old idea, but not one to be dismissed.
Not one to be dismissed, absolutely. So the question is, has the situation changed? And the situation has certainly changed. So multicores have arrived. This is a big deal. I mean, Microsoft now wants to exploit parallelism, And there can be no bigger indication than this, And there is explosion of cell phones. And if you don't understand what that means is economically, there are 100 million PCs that will be sold this year, and 950 million cell phones that will be sold this year. This is the same kind of transition that is taking place that happened in early 80s, when we went from mainframes and mini computers to micros, right? So what happens there determines what happens everywhere else. So it's quite possible that what happens on these small devices, handheld devices, will determine the architecture of everything else, just because, of the numbers. People are willing to invest a lot more money into this. Explosion of game boxes. Sorry?
The explosion of laptops is also happening.
Yeah, but that number is 100 million, right? While cell phone is 950 million. So at least in 2000. Right. Absolutely. So look, if I'm talking to you as a teacher, I mean, my message to my colleagues in the department is, it's no longer good enough to say, well, we'll teach you parallelism when you're a sophomore. right? I mean, it is the thing that people want to deal with. You know, they say, what do you mean you're telling me how to program one processor? You know, I have 10 of them in my pocket, right? So I think we have to deal with this. You know, how do we introduce parallelism? What method we should have for teaching parallel programming, you know, so that that is the default programming model in your head. So it's all about parallelism now. No longer an advanced topic. It has to be the first topic. Just another word of caution in this. So let's look at cell phones, right? So mine, you know, has some bugs in it. So sometimes it misses a call when I'm surfing the web, right? It doesn't ring. Okay, so this is the deep question now. So whose fault is it, right? For example, to what extent the phone call software should be aware of web surfing software or vice versa. So now you have to understand how these things are done. Of course, how the phone calls are made, that software has been evolving, right? You can look at it over the last 15 years, you know, and you'll be able to trace a continuum, you know, how phone calls are made in that. And that's not trivial amount of software on your cell phone. Well, when it comes to web surfing software, I can guarantee you it was not written from scratch, right? People went to your PC, they say, what do you do on your web? You know, they take all that software, say, let's port it on the cell phone. Now, the guy who wrote the web software never thought you'll be talking on telephone, you know, while you're surfing the web, or at least not on the same device, right? And vice versa, the guy who wrote the phone software never thought, you know, that you'll be surfing the web, you know, while you're talking on the phone. I mean, even in 1995 or, you know, 1998, if somebody had said you'll be surfing the web at the same time, it would have sounded pretty bizarre, right? It just wouldn't have made. So, is it merely a scheduling issue? So this is the answer you use. You know, they didn't process the interrupt properly. I'm sorry, this is not just a scheduling issue. I don't even know the semantics of this. So for example, if you're surfing the web and the phone rings, do you really want to stop surfing the web and pick up the phone? I mean, what's so special about phone? I mean, there is nothing being indicated from the language point of view, right? It may be application requirement that you want to stop it or not stop it and so on. Is it a performance issue that, it's because you have only 2 processors in this. If you had 4, this problem will go away. Or if you could just run it faster, it will go away. I don't think any of these answers are right. I mean, the bottom line in this is sequential modules are often used in concurrent environments with unforeseen consequences. So your mindset has to be that I'm going to put together a parallel program with lots of existing things, right? Because you can't keep giving the answer, let's just rewrite it again from scratch. You know, because the amount of software is so enormous in this. What we should worry about now is how we should design these modules, how we should write pieces of software or design hardware so that we can put together an ensemble of them, you know, a collection of such modules so that they do something useful, right? And it's all about parallelism, you know, how to do all this in a parallel setting. Okay, so new goals as opposed to the old goals. So I don't want to think in terms of decomposition. I don't want to think in terms of, here is my clever algorithm, right? How do I decompose it so that this runs here and this runs here and so on. Instead, I want to think in terms of synthesis, that you have already given me lots of modules, you know, which are very useful, which perhaps are written by domain experts. They know something about that stuff. And can I put together a bigger application very quickly from it? And, you know, another favorite example of mine in this regard is, you know, FFTW and linear algebra packages. Both have been optimized to the hilt, right? And if somebody gives you an application which calls enough FFT and uses enough linear algebra, I guarantee you that program will not be easy to write, in spite of the existence of both these packages, right? Which are extremely well optimized. So there is something we are not paying attention to, is how do we bring parallel modules together in such a way so that the functionality, the performance, etc., are predictable in some sense.
I'm sorry, what's your point, Arvind, because your point, I think we agree with your point, I just want to make sure I understand
Yeah.
your point. That that FFTW linear algebra is not enough, and so there will be.
No, I think it's very well done. FFTW, linear algebra is very well done, but we still haven't provided any good way of thinking in terms of two parallel things. What happens when they interact,
Oh, okay.
right? So if my program is calling FFTW often and then it's calling linear algebra
Right.
often, right?
So actually, that you weren't here when I mentioned that, but I was actually bringing up the point of linear algebra and FFTW working together, just working.
Exactly.
That was the performance issue. It just hasn't worked.
Right.
So it was the very same sort of
Exactly, absolutely. So I'm saying in that sense, you see, this is a different way of thinking, because the old way of thinking was, well, give me your application, now let's decompose it. The point is, I don't have experts, who can write FFTW as well as Matteo wrote it, or whosoever linear algebra packages are being written. I want to use those things. I want to synthesize large parallel programs quickly. Yes?
How does the Apple iPhone work with the
Sorry, how does?
iPhone?
Apple iPhone.
Apple iPhone.
Yes, they have an operating system on there, and
I think it will be, I think from our point of view, that's the same thing. It's just that the user interface is guaranteed to be far superior, because in my phone, when I see the icons, I'm a techie and I still can't understand half of them. Right? So I like Apple's idea, phone, pictures.
So Apple has a way the Apple might deal with that is it's going to not let anybody program it. It's going to have a very restrictive developmental program internally. So they can basically say, instead of I'm going to take this person's and this person's put it together, they will try to do everything in one unified way. So to some extent it might work. But then you suddenly realize Apple can't hire enough programmers to keep up with all the needs in there. So the minute you start to have other people plugging things in, things break.
But if internally that software is,
so is there something parallel going on in there?
it's guaranteed there will be parallel stuff going on there. Guaranteed, because all the communication stuff has to go on in parallel with the computation stuff. So, phones have to do lots of things in parallel, just if for no other reason, just because of power. It takes less power when you do things in parallel as opposed to when you do it sequentially, because then you have to run much faster, in that. Okay, so a method of designing and connecting modules such that functionality and performance are predictable and must facilitate natural description of concurrent systems. A method of refining individual modules into hardware or software for systems on a chip. So refinement is a word, it's a highly technical word. What that means is that you have written a program and you may want to rewrite it, but nobody can tell from outside that you rewrote it. All right, so you refine it, and you can refine it into hardware. You may implement it in hardware in this. As opposed to transformation. Transformation is automatic. We're doing something, it's guaranteed, it's correct. Refinement, you may have to work a little bit more to show that it's correct in some sense. It's a correct refinement of whatever you were doing. So basically, just to get the application going, which, as Alan is pointing out, is the major task, and this is true regardless of what people say. When you get to complex system, if people start talking about performance, you're 90% there. That means the damn thing works, right? So even though people may say, performance will be lousy, most of the energy is just consumed in getting it to work, right? So never forget that. So a refinement idea becomes very important, because you want to take as many things as possible which are available, right? Make it work, and then individually refine, modular refinement of things.
Maybe just also underscore, just to emphasize what you're saying. Our salesmen will go and say explicitly that they can sell a factor of 2 in performance, just like you were saying.
Yeah.
That just a factor of 2 on 100 processors, whatever. They can sell that if it works. If it gives the right answer.
It's the ease. It's the ease and confidence that it's really doing what you expect it to do.
It's really performance second, ease of use first. We've got it backwards in academia.
A method of mapping such designs onto multicores. Right? So why multicore problems becomes hard? And this is where hardware and software starts diverging a little bit. So what happens in hardware design, everything is in parallel. right? I mean, it's sitting right there, this block does this block does that, right? So there is no confusion in your mind, what's going on in parallel. If you have to multiplex something in hardware, that, oh, first we'll do this, then we'll do that, that's also expressed explicitly in the design. Software is not like that. Software, I have n threads, but I have only 10 in my hardware. So there is another layer of, software or operating system or whatever you want to call it, runtime system, whose sole job is to virtualize or to do time multiplexing of underlying resources, and that makes the problem harder. That makes the problem harder whether you're doing it in a way that preserves some performance goals, whether you're doing it so that you won't cause deadlock. So there are many, many issues that come up in this. And basically, when I said this is an ideas kind of a talk, I do know how to do this, right? And I still haven't worked enough on this problem of how to, take this kind of methodology where I can write these parallel modules, compose them, how to map it onto multicores. Okay, so now let me tell you something technical about this stuff. So this hardware-inspired methodology for synthesizing parallel programs. So now I'm going to use some fancy words. So this is a rule-based specifications, or what I call guarded atomic actions. I will explain in a second what that means. And it will let you think about parallel systems in a very different way. So it's like saying, look, if this register is 2 and this register is 3, you can add them and put them here, 5, right? And you can do this any time you want, right? So this is like a rule, invariant. You're saying, I don't care what's happening in the machine. This is always safe to do. Now, what I'm going to ask you to do is take a huge intellectual jump from this, that if you give me enough such rules, you would have completely described the hardware, what it does, right? Now, why am I thinking like this? Because if these invariants are stated properly, it's always possible to understand the behavior of the system as if one thing at a time is happening. When 2 plus 3 is becoming 5, if you want, you can have this mental picture, the rest of the world is frozen. Nothing is changing there, only that change is taking place. And you can think in terms of these small, small changes, and all legal behaviors will be explainable as some sequence of these changes. It's possible to describe all kinds of hardware, using things like that, composition of modules with guarded interfaces. So this is the language called BlueSpec, and it has very strong echoes of a language that was designed in 80s by two guys, Chandy and Mishra. The language is called Unity, right? But they never used it for hardware design. I mean, their goals were different, and they didn't really have a concept of a module in that language. So let me show you 3 examples here. Greatest common divisor, just to get off ground, and then I will show you 2 very different problems, airline reservation query problem and the video codecs, H.264. We won't have time to get into ordered list, but if somebody wants to discuss that, I will be happy to show you. Okay, so now let's look at how do I think of my design of my program in BlueSpec. I always think in terms of a bunch of modules, right? And what's a module? A module is going to have some state elements in it. If you're thinking software, just think each module guards some variables which nobody else can touch, right? You are the only one. So you have variable XYZ, he has some ABCD, etc., right? So each module has some, so that's what I'm showing in red. If you were thinking hardware, think of these things as stateful elements like, registers or flip-flops or memories, right? But the main point is, if it is here, then it's not here. I mean, these are, you own something, this module owns something, this module owns something. One. Second thing is, every module has internal rules for manipulating the state. And the rules are always going to be of the form that if some condition is true on this, you're allowed to make the following changes to that, right? So that's what the rule looks like. Some condition, if it holds, then by action I mean change the state of those variables. And it's all or nothing. So if you have two variables and if you want to change both of them in a rule, then the execution of a rule means either both of them will change or neither will change. There is nothing in between you can see, right? That's disallowed by this model. All right. Now, rules are, of course, I mean, the reason I have modules is they're not totally disjoint. You can actually access the state, both read it and write it, but you can't just arbitrarily reach it and do something. You have to go through some interface methods. The moment you talk to some other modules, so this is the standard information hiding principle, abstract data types, whatever you want to call it, so there is an interface through which you will enter. And if you're just reading the values, I think we call them read methods or value methods. And if you're going to affect the state of another modules, we'll call those action methods, right? Because you're actually going to change the state in some module. So now, very strange execution model here. Very, very different from sequential execution model. So repeatedly you do the following. You pick a rule to execute, any rule, I don't care, right? And select a rule to execute, compute the state, what updates should be made, make the state update, and then go and do it again. So repeatedly you do this. So this is a highly non-deterministic thing, right? Select a rule. I mean, there may be gazillion rules in your system, right? So primitives are provided to control the selection if you want. But it's a detail that we won't get into. So does everybody get the model right here? That you have a lot of state elements and you have a lot of rules. Many rules may be applicable. Pick one of them to execute, right? Execute it, that will change the state. Ask the same question again, which rules are enabled? Now, pick any rule amongst them and keep doing it. Now, semantics say one rule at a time. In any implementation, we're going to do many, many rules in parallel, right? But you don't have to worry about that. That will be done all automatically, right? That we can do many rules in parallel. Okay, so now let's look at GCD. So this is an ordinary GCD program. You can write it in any language you want. If y is 0, then x. Otherwise, if this is greater than GCD, or yx, otherwise, you subtract. Okay, so no problem, and I'm sure you know how it executes. So if I was to take GCD of 615, if you will see, there is a recursive call that will go on because 6 is less than 15, so it will be this. You get this, and you get this, etc. Ultimately, you get 3 as an answer. Everybody's with me? You all know GCD. You can all write it in your favorite language. Now, the question is, what does it mean to execute this program in a concurrent setting? We were not thinking parallel or sequential, right? This is GCD, Now somebody says, someone, is teaching this class, says, run it in parallel. You say, what do you mean, run it in parallel? Oh, you mean that maybe I should try to do several GCD calls, recursive calls in parallel? That also doesn't make too much sense in this, right? Perhaps this is what someone meant, that if he has some program where there are 2 calls to GCD, right, he would like you to do those 2 in parallel. Right? I mean, what does it mean to do GCD in parallel? Now, let me contrast this with how you would think about this problem as a hardware person. So your job is to build a GCD machine. You're going to make millions of dollars. This GCD is very popular, right? So you build this GCD machine. It has 2 inputs. It has an output. And this will be my module. I'm going to sell this intellectual property, right, to everyone. Okay, so now let me talk of parallel invocations of this. You see, in hardware, there can be no confusion. Either you have 2 GCD boxes or you have 1 GCD box, right? I mean, you can have as many boxes as you want, right? But there is no confusion about that. How many GCDs you have. So in some sense, if you have many of them, you're talking of independent calls, right? Who knows what's about recursive calls? I mean, that's internal story. That's a different level of question. So this question will automatically get asked. In hardware, you will ask the question, does the answer come out immediately, right? Does it come out in predictable time? Why is this question important? Because if it's going to take some time, then while it's computing, the question I'm going to ask is, can I give another set of inputs? Are you with me? Right? I mean, that's a legitimate question to ask. You know, if it's going to take half an hour to compute the GCD, can I give it another input, you know, while it's thinking? Can the machine be shared by two different users, right? Can it be pipelined? So you agree that all these questions are meaningful in hardware setting. And I claim all these questions are also meaningful in software setting. We just don't think like that. This is exactly the problem we are having right now. You know, when we say that we have optimized something and we call it again, right? We think of it as starting afresh. Maybe not, maybe not. You know, maybe we should think of it in terms of resources. You know, and the point I want to make is, I want to think of GCD module as a resource. Even in software, I want to think of it as a resource, so that there is no ambiguity in your mind whether you have one GCD or you have two GCDs, right? If you're going to multiplex it, we'll write it differently. If you're going to have two independent ones, you know, which can go on in parallel, we'll write it differently. Okay, so that's the idea I want to borrow, you know, from the hardware side in this. So how would you do? Yes.
So how would you decide how many GCDs to instantiate? Would that be, in this model, left up to the programmer?
Well, you see, that's the big difference in hardware and software, that in hardware, you have no design until you have taken that decision.
Right, but in software, you'd like your, I mean, hardware designs, once it's built, it's built. Software designs, you want the same module of software to seamlessly run on different kinds of hardware.
That doesn't mean that I can't recompile it or can't, you know, resynthesize it or something.
Right, but if you're...
So it may be same source description in software.
Right, if your source description specifies 2 GCD modules,
right,
and you have 8 cores,
right,
you're not necessarily going to take very good advantage of this. So how do you...
No. The way I would like to think about that is that it will be highly parameterized code, and you will plug in some information like that and resynthesize the parallel program.
So the software or some sort of macro meta software has to determine the extent to which the problem should be distributed.
Well, you can think like that, but really this integration will be much tighter than you think. So for example, let me just give you some more insight from the hardware side. So in the hardware side, it's standard practice that I will have some RTL code, I'll have some code, right? And I plug in the library. What kind of gates have I got? Have I got 2 input gates, 4 input gates, whatever, you know. There may be a huge library, right? The same code can be compiled using different libraries. So you choose something at synthesis time. Another thing that will happen in hardware is what is called generic statement. So you may have a loop which instantiates a register file with n registers, right? Which may conceptually make sense, it may make sense in simulation, but when it comes to synthesizing it, you have to specify n, right? So I'm going towards that kind of methodology, that you will have highly parameterized code, but many parameters you will have to specify before you will say, now my program is ready to run on this parallel machine. And this is totally unexplored yet. I mean, this is just, as I said, this is an ideas level thing.
So this adds a problem that is not in traditional hardware synthesis, namely picking all the ends. Ideally, you wouldn't want to have the programmer to come up with creative algorithms, because they're going to have lots and lots
Absolutely.
of ends.
You know, that we may have lots of defaults, we may have other level of smart programs, you know, which look at this and they instantly go and set many parameters. You know, so there will be a practical side, many issues like that. But main point I'm trying to make is that I really want to synthesize, I want to instantiate a program, synthesize a program for a given configuration, right, of hardware. Let's look at the GCD in blue spec. So, you know, if I'm going to find the GCD of 2 numbers, I need 2 registers, X and Y. So that's what this is. Make me a register think if you want, make me two variables, make me a variable x and y, initial values are 0. So this is what is called the state of the module, right? It knows about x and y. Nobody else knows about x and y, right? What is the dynamics of it? How do I compute this? So internal behavior is being described, and this is exactly what you saw earlier. It's saying that there is a swap rule. If x is greater than y and y is not equal to 0, then you swap x and y. So this is a parallel composition. X gets y, y gets x. In this system, all the reads take place instantaneously, and then you do all the writes at the end of it, right? So don't read this sequentially. You read x and y in parallel, and then you go and update x and y. Does this rule make sense? I mean, if you know anything about GCD, if x is greater than y, then we're going to swap it. And subtraction is if x is less than or equal to y, then y gets y minus x. So this is very interesting. Now you have two registers, x and y, and I've given you two rules, and I'm saying you can apply these rules anytime you want. Just repeatedly keep doing these rules, right? Now, what does the outside world know about this? What do you want to advertise about GCD to the outside world? You don't want to give away your secret. This is your intellectual property of how you're computing the GCD, right? You just want them to use GCD. So the outside world can say, oh, find me, start it, right, with A and B. X gets A, Y gets B. It's going to give you two parameters. But, we may be busy computing, right? So we have a guard here which says, if y is 0, this is all internal, outside world doesn't see this, right? If y is 0, then, only then you can start it, otherwise you can't start it. Otherwise it means it's busy computing. Okay? Similarly, when is the result available? When the y is 0, then you have the result, and you will return x. That's right. So that will become more sophisticated. And that's exactly the kind of decision I do want the designers to take, because you may want to put a FIFO, right? You may just keep spitting out results. You can make it as sophisticated as you want, tag it if you want, right? No predetermined thing, This is just. So first question I ask you, what happened to those recursive calls? Right? If you go back to the previous slide, there was, we recursively called GCD, which you are all comfortable with. There is no GCD call here. Right? So there is a notion of a cycle event or something, right? Look at it now, update it, look at it again. So there is like an infinite loop here, which is always going, right? Which is exactly how hardware works. Right? You're always, it doesn't have to be synchronous, but if you want to have a simple model in your head, just think there's a clock, look at all the state, pick one rule to execute, update it, then it's the next clock cycle, right? Keep doing this repeatedly. It's details here, but I can take such a description and actually produce that machine for you, right? Which does the GCD. What I'm much more interested in is, this is how I want to think about my GCD now. So I've hidden everything inside it, right? And it has two methods, start and result. And there is a very strong notion of when a method is ready, because it may be busy computing. It doesn't want to listen to you, right? So there is this notion of something being ready. And if it's an action method, then you are only allowed to enable it when it's ready. So this is a high-level protocol that compiler will enforce. It will never, ever set this, it will never execute this unless it is ready to be executed. And of course, when you're going to enable it, then you have to give me two arguments that go with it. And what does this ready mean? The result is valid, right? So if you're into types, etc., this could easily be maybe type or something, tag union type, that valid bit is being coded here. So really, to the world, we are, just advertising this interface, that there is a GCD interface, and it has two methods: an action method which is called start, and a result method, which is just a value kind of a thing. And in order to do this, you have to give me an int A and int B in this, an end of interface. Now, this is borrowing a lot from modern programming languages. So, for example, I can easily make it polymorphic. It doesn't have to be ints here. You know, what is the meaning of int? I can actually, you can specify the type in this, right? So it will be type T, A's of type T, B's of type T, etc. What are the examples of type T here? It could be a 32-bit integer, it could be 16-bit integer, it could be 17-bit integer, whatever you want, right? Whatever makes sense. So this is the kind of thing that you always take care of when you synthesize things. It won't synthesize until you specify the type, but the description remains the same, right? And you will instantiate it for a given type. This I'm showing you for one reason. If you were coming from the hardware side, really these ideas in types and instantiations, etc., will get very sophisticated. I mean, this is getting as advanced as you can have in software. The other very interesting thing is, and this is the abstract data type kind of thinking, you can go and completely change the implementation of this, right? If you have a cleverer algorithm for doing GCD, fine, go ahead and do it. It doesn't affect the users of this, right? So this is a very important property for composition, right? All I insist on is that every method has this ready thing coming on, so that I don't make mistakes in wiring it, right? I will invoke this method only when it's ready. So in some sense, if you forget about the ready thing, I'm just borrowing ideas from object-oriented languages. You have a class, you have methods on it, and all I'm saying is, you should manipulate the state in a very systematic manner, using these methods. But then I'm injecting some hardware idea here, which doesn't exist in software today, that is, a method may not be ready, right? And even that can be captured very abstractly and done properly in this. Yep.
So the communication between modules are asynchronous by nature. So if you want to basically synthesize the hardware, you may achieve better efficiency by having sort of synchronous protocol by taking the output after a certain number of cycles, predetermined number of cycles.
Right.
That is possible.
I think yes, that will be a low-level detail. That if it is synchronous, then you will actually try to manipulate it like that. But
we have about 5 minutes. Just hold the question.
okay, right. Okay. So let me just quickly say what the language is. So you have modules, and you have state variables, and you have rules, and you have action methods and read methods. What I wanted to show you is what is the language of actions, right? So when I write an action here or an action here, what is it? So simplest action is assignment to a variable, right? Assignment to a register. This is a conditional action. So if predicate is true, then do this action, otherwise no action, no change in state, right? This is a parallel composition. Do A1 and A2 in parallel, right? Sequential composition, the effects of this are visible to this, etc. This is a call to a method of another module. And then there is a guard. And you have an expression language, which is, there's nothing special here. So this is just simply, you can have, you can read a variable, you can have constants, these are just names, and you can have, there's nothing special going on here. Let me explain you guards. So people find guards versus ifs confusing. And this is one way to understand it. So guards affect the surroundings. So if I wrote here A1 when P1 in parallel with A2, think of guard as something to do with resources. I really don't want you to do A1 unless P1 is true, right? P1 may reflect that the module was busy. Whatever, some predicate here. But I want the effect of this whole thing to be atomic, right? So if any part of it can't be done, then the whole thing can't be done. And therefore, the effect of guard is as if you wrote A1 in parallel with L2 when P1. In other words, guard on anything becomes guard on everything in that parallel composition. Do you understand what I just said? Right? That this is very important for composition of guards, because I want the atomicity of the whole thing to be preserved. So if anything can't be done, that means the whole thing can't be done. On the other hand, conditional action is just conditional action. So if I have if P1 then A1 in parallel with A2, well, that's like saying if P1 was true, then I want to do A1 and A2 in parallel. Otherwise, I just want to do A2. So there is a very big difference between conditional actions and guards. Guards are something about resources I need it for proper composition of atomic actions. Yep.
I had a question there in the previous slide. So are they entirely equivalent though? Because this is maybe a low-level question, but in the first case, so the first on the statement on the left, can't you start doing A2 and then roll it back or something? Whereas in the second case you can't.
I think there may be many tricks you can play in implementation. You can be optimistic.
Right. So
you can roll back.
Not equivalent.
No. There will be semantically. This is defining the semantics. This is the algebra. This has to be true because I'm saying this is what a guard is.
Right. So they're semantically equivalent, but not necessarily equivalent in terms of what the implementation might do when it sees the two things.
Well, that's probably not the right way to say it. Semantics are being defined. You have choice in implementations. Right? I'm not telling you how to implement this. Yeah. Let me go on with this. So here is a problem that was posed to me by Jaidev Mishra. This is quasi-realistic problem. Okay, ask for quotes from 2 airlines. If one quotes below 300, buy immediately, because 300 sort of is the cheapest ticket you get these days, right? Buy the lower quote if over 300. But at some stage your patience runs out. I can't wait anymore, right? So after 1 minute, buy from whosoever has quoted. Otherwise, flag error. Is this a realistic scenario? Now you can express it using threads, and you can write a scheduler, to do this, etc. Those things are not as succinct as you would like. You'll be surprised in this simpler problem how complicated and how many questions will arise if you express this as a threaded computation. Now let me show you what you would do in BlueSpec. Okay, so we are going to make a module which does what? Make get quotes, right? This module's job is to get quotes. So what kind of state elements do you expect it to have? Well, airline A may be quoting some value, airline B may be quoting some value. Whether we are done or not, there's a timer, right, which we are going to be bumping, etc. And there will be rules, so get a quote from A, which will be when not done, do something, executes when A responds, right? Get B, timeout, etc., etc. There are many rules of this sort. Let me just show you one method. Okay, so method is, this is how you will start it, right? You have this module get quotes, and you're saying book me a ticket, and this is your request R. Now, obviously, this can only be done when the module is not busy, right? If module is busy, then you can't do it. So what will you do when you get such a request? Tell me if this makes sense. So what is this saying? Try to get a request from A. In parallel, try to get a request from B, right? Now you are busy, right? The module is busy, so done equals false here. And I'm initializing this. I'm just saying that the A code right now is infinity and B code is infinity and timer is 0. Fair? Right? And when will I get ticket? Well, when done, then you'll return the ticket from this. Now let's look at example of a rule. So you may have a rule like this, right? Pick cheapest. You see, the interesting thing in this is you'll be able to read this independently of what else is going on in this system. And let's see, what does this rule say? Is it succinct? rule says when you're not done, right? And if the code from A is not infinite, that means A has quoted, right? And B has also quoted, right? Then what should happen? If A is less than B, then buy the ticket from A, otherwise you'll buy the ticket from B and you're done. I'm not going to write all these rules, but I think you should be able to really, I'm certain you can write these rules. This is, what's happening here is just separation of concerns, right? It's all concurrent stuff, right? Yes?
How does associativity of the
Parallel?
well, like, for lack of a better word, the pipe and the and.
Sorry, say it again?
So at the beginning there's an ampersand, right? How does that interact with the...
Can you hold that question first? We have to run out of tape, so we
Oh,
have to stop.
So the ampersand after not done,
Yep.
that is like what sort of ordering is that?
It's just, I mean, associative, commutative kind of thing, you know.
Okay.
It's all happening in parallel.
Heat has to happen all once.
Huh? This thing, right?
Yeah.
I mean, think of it like these are variables, right?
Mm.
And you're checking their values right now. So it's just a combinational kind of a query that you have here.
So I guess when you're checking, there's no activity happening. So you freeze
That's
the
right.
system, you check, and when you freeze the system, it doesn't matter what order you check.
So I guess what I'm trying to get at is that the whole block at the top is executed in parallel with
Absolutely.
the block at the bottom. Okay.
No, not lots of things that happen in parallel
Okay.
in this, right?
But in some sense, you freeze the world,
Exactly.
check the conditions, and then you go to the read the world.
Yeah.
So and then you go to the active. So it just kind of phases.
Right. Okay.
Conceptually.
Now, I just want to show you this because this is completely different from airline reservations, right? You know, H.264, this is a codex that is being used everywhere and will be used even more. And this is a typical data flow diagram you will find, you know, for this kind of thing. You don't have to understand anything but about this, except that these things, conceptually, you just have FIFOs for communicating between them, right? And in all such things, the goal is that it has to be able to sustain a certain amount of rate at which data is to be processed, and it's usually forgiving in terms of latency. So if you know, latency increases a little bit here and there, it's usually okay, right, when things go in and come out. A data flow like network. And another reason why this example is fascinating is because it's done regularly both in hardware and software and any mixture of the two. So for example, when it runs on your PC, you know, it's being done 100% in software. And when it's being, you know, there are, I think on iPod there is special purpose hardware for doing it, and therefore the battery can last much longer, right? And on cell phones it's kind of in between in this. And it's a question of what frame rate you want to process. If you're processing very high frame rate, then it'll have to be done in hardware. So when we got into this thing, you know, we said, okay, we wanted to build hardware for doing this, and reference codes are available. It's 80,000 lines, and it sort of gives you a heart attack. You know, you read this and you say, whoa, and it doesn't meet the performance. You know, I mean, that reference code, if it ran on your laptop, you won't be able to watch a movie, you know, with this. And then there is the Linux version of it, which gives you even a bigger heart attack because it's 200,000 lines and many different codexes are mixed in this. The biggest problem here is none of these codes reflect that picture I showed you on the previous diagram. Because the way people approach it in software is they take some input from here and they push it as far as they can, right? And that's it. Then they will take the next input and push it. So different boxes keep modifying it, as they see fit. And as a reader, you can't tell that, oh, this is this part and this is this part. I mean, there are no FIFO queues. Why? Because FIFO queues are expensive in software. It will involve copying. You will write it here, then you will read it again, which is a bad idea in software. So in some sense, the software way of thinking already entered, in this style of coding. There is no model of concurrency, so it's not clear to me when you give me that code what all I can do in parallel in order to preserve the semantics of this. I mean, the problem is much, much harder here, really. So you will just do some high-level analysis of the code, but you have lost a lot of information that was all present in the source, could have been present in the source. And my claim is it can be done differently. So if you, this has been done by Chung Che, and this I'm showing you a month-old slide, but he has done a lot more work since then. And the total code in BlueSpec is 9,000 lines for this, contrasting it with 80,000 versus 200,000 kind of stuff. And this is telling you the amount of code in various, blocks in this. And, since it's done in BlueSpec, you can take it and you can go and implement it all in hardware, so you can synthesize it. It actually does now 45 frames per second, actually 90 frames even per second today, so this is a month old. This is the main point. Once you have done this, now you can refine it. You have a different preference. You say, oh, I want to do this differently. So you can go and rewrite any module again, right? It will be very, very easy to do this in the system. It is very difficult to do this in the reference code. So that's one point to be made. The second thing is, you don't have to do everything in hardware. If you wanted, you could have implemented any part of it in software. So you can take the same kind of a description and generate software from it as well. So each module can be refined separately. Behaviors of modules are composable. You can take these things and it's predictable what will happen when you compose these things in terms of performance, and in terms of resources also it's very clear what's happening. In hardware, the resources will be area and time and so on in this. So takeaway, parallel programming should be based on well-defined modules and parallel composition of such modules. Modules must embody a notion of resources and consequently sharing and time multiplexed reuse. This is a controversial point. And guarded atomic actions in modules with guarded interfaces provide a solid foundation for doing so.
Thank you. I know we ran a little bit late, so if you have questions, you can ask, but if people have to run.
Yep.